Hi, this is Monica Yeager, and this is my Physics 2211 lab report on constant velocity. So, I want to give you a brief introduction to the rest of this video. Newton's first law states that an object will not change its motion unless acted on by an unbalanced force. So, if an object is at rest, it will remain at rest unless a net force acts upon it. An object in motion will stay in motion unless a net force acts on it as well. Newton's second law, or also known as the momentum principle, states that the acceleration of an object is directly related to the net force and inversely related to its mass. In this experiment, the net force will be briefly introduced, and the net force will be zero at constant velocity. These are the models and formulas that we will be using later on in the slideshow. First off, we have the position update formula. This is final position is equal to initial position plus average velocity times delta t, or change in time. The velocity update formula is final velocity is equal to initial velocity plus acceleration times change in time. And then we have Newton's second law, which is force is equal to mass times acceleration. By plugging in acceleration, which is force divided by mass, we can derive other formulas from Newton's second law. So these force body diagrams that we have on the left show increasing velocity and constant velocity. Increasing velocity has a normal force with the arrow pointing up, gravitational force with the arrow pointing down, and applied force with the arrow pointing to the right. Because normal force and gravitational force cancel out, we're only left with applied force, which causes acceleration and results in increasing velocity. Constant velocity only has normal force and gravitational force, which cancel out, which means there is no net force. To give you an example of this is a tracker video of the system, in this case a ball, and the surroundings, which is me pushing the ball. On the top right, you can see a graph. On the x-axis is time, on the y-axis is distance. As time increases, distance decreases because in this case, the axis is on the ball that starts off in the right and moves to the left. And the left is negative, therefore it decreases. So this is the coding part of the project. The initial conditions I set as initial position, which is 0 in the x position, 0 in the y, and 0 in the z position. The initial velocity I found as negative 0.3607 meters per second. I found this number by calculating the average velocity, so the total distance divided by the total time. I set the mass of the ball as 1 because it cancels out, so essentially this number does not matter. As you can see, I set time as 0. That's where the time clock starts, and delta t as 0.01. This is the size of each time step. In the while loop, I put t is less than 2.8 seconds, since that's a total amount of seconds. And fnet, I put as 0 because there's no net force. In the velocity line, I use the velocity update formula, and in the position line, I use the position update formula to calculate the position. So these are the results. As you can see, it's similar to the tracker video. As time increases, position increases, but in the negative direction. In the velocity versus time graph, the velocity stays constant. So there are some discrepancies between the model versus the experiment. As you can see, the tracker is not perfect. This is probably due to some inconsistencies like human error, friction, or some applied force that wasn't taken into consideration. So here's some follow-up questions. Can net force really be 0? Ideally, if it is in equilibrium or the forces are balanced, they will cancel out. But however, this is unrealistic because there is always going to be some friction, and this doesn't always cancel out with the applied force. One will usually be bigger than the other. What if the ball was moving right instead of left? If it was, then same thing would happen, except it would, as time increases, position would increase in the positive direction. What if our axes were flipped? If our axes were flipped, same thing would happen, just as time increases, position will still decrease in the negative direction. However, the slope would be positive. So, in conclusion, what does it mean if we assume the net force is 0? This means that all the forces acting on the object are balanced, resulting in no acceleration or change in motion. So, for example, if the object is at rest, it will remain at rest, but if it is in motion with constant velocity, it will continue to move at that velocity. So, if acceleration is zero, if there is constant velocity, the net force acting on it is zero or balanced. There would be no external forces causing a change in its motion, and that's what it means to have constant velocity.